Okay. Hello, everyone. My name is Changxin from Affiliation on University of Southampton, UK. Today, I will talk about repeat prototyping of organic electrochemical transistor for the future e-textile. So it's a quick overview. The first part is introduction, some e-textile example, and why I will do it. And then it's organic electrochemical transistor as a dispenser printer, and part 2 is fabrication method for OECT, and then is the result, and final is a conclusion. Okay, let's quickly view the e-textile example. There have some example from my research group past over a year. They have some watch display, electrode, and any sensor. So specifically for this one is a printed electroluminescent watch display, and this one is a motion sensor. So both of these need a silicon chip and the controller or decoder to process the data. So for the future e-textile, we want to get more flexible because all of the silicon chips are hard, is unbendable, but for the future e-textile, we want a flexible one. So organic electrochemical transistor, or we call OECT, it's a flexible. We can do this. So this picture shows the OECT, how to work. When the gate is off, and semiconductor have some ion, like this one, and hole can jump in this ion, so it can flow the current. And when it's on, the electrolyte, some ion, go into the semiconductor like this. It's a balance of the ion. It's a reaction. So that's why we call this a chemical transistor. It's a reaction here. And then it's off the current flow. So the OECT have some advantages. The important one is flexible. So all the material, the gates, electrolyte, semiconductor, even the substrate, all this is flexible. And then it's a low operation volt. It's less than 1 volt, so it can confuse less more power. And then it's a high transconductance, so it can use for the bioelectronics, for the sensor, for the signal amplifier. But it also has some challenges. First one is a slow switching speed, almost to the microsecond to the second is very slow. So and another one problem is stability. So it's very sensitive with oxygen, moisture. And the final one is device size. It's more big compared with the traditional transistor. So this is a dispenser printer. So why I use this one? Because I tried to use screen printer before, but I found screen printer, if I change the design, change the structure, well, I have to buy the screen, use more cost, so use more money. And it's very slow. I need if print one layer and change another one screen, another one screen, another one screen, so it's very slow. And another one is inkjet. Inkjet is very quick and very easy to design, but the ink is a specific ink. So the dispenser is combined of advantages of the inkjet and screen printing. You can see here how to work. It's like squeeze the toothpaste, and it move, and how to the ink to going out is controlled by the computer. And this one shows a multi-layer structure. Before my research group down, you can see here it's complex multi-layer structure, lots of layer and different material. Do the EO lab, and this one is EO lab with proximity sensor. When we hand to close, the lamp will be light. So why I show this? Because we can use dispenser to do the multiple layer structure. Okay, go back to the OECT. So this is a OECD structure, vertical structure. We can see it's also a multiple layer structure and use different materials. So go back to the fabrication. So the first is print the electrode, print the gate, drain, and source, use silver ink. And then is print the channel, P.PSS. And then we use the carbon electrode to connect with the silver and the P.PSS. It's for the, if the silver contact with P.PSS directly, the silver will be oxidized by the P.PSS. So the carbon can protect the silver. And then it's electrolyte. This is a UV curable electrolyte. And then it's a P.PSS as a gate. This is for the supply the ion to exchange with the electrolyte. If we just use silver to connect with electrolyte directly, the silver can't supply the ion. So this is OECD printing the PET pen film, and the green is because the substrate under the pen film is a FR4 board. So it's why it's green. So, and this is circuit for the test the OECD. So the VDS is hold to 1 volt and scan the VGS to 0 to 2.6 volts, and then we will go to the IDS and VGS curve. You can see here is two typical LECT, 1 and 2. The black one is 1. Black one is it have the high current ratio. The red one have a small one current ratio. And the next is switch time. You can see the LECT1, the red one, have the big IDS, but the switch time is a little bit slow. It's almost to 2 seconds. But the blue one is lower IDS, but it's very quick. You can see here it's almost 200 microseconds. So when LECT is open, the ADS is affected with channel resistance. And channel resistance is relevant with the thickness of the channel. For this one, it's thickness of the P.PSS. When the OEC is closed, so IDS, there have some leakage current. This liquid current is flow as the drain and source, the carbon connect with electrolyte. So this have the leakage current. And switch speed is relevant with thickness of the channel. If the channel is more big, the time also will, switch time also more big. This one is OECD printed the PET film. You can see here it's flexible. So to sum up, we have successful get OECD use dispenser printer. So this is a repeat prototyping method. And the typical on-off current ratio can up to the 3000. And typical switching time is to off is 200, to on is 1 second. So for future work, it's optimize the structure, optimize the material for get the more quick speed or big current ratio. So for the future, the final target is get the OECT Yong. Is my PhD project. Print the OECT in a single Yong. So that's why I need, for this research, I need to find a fast printing way to make sure which structure I need to use, which material I want to use, which is more better. Okay, and thanks for the funding by the STELAC project, and thanks for Peter for the material supply and technical advice. Thanks everyone.